Welcome to the photon factory. Are you here for the tour? Oh, 1 second. You'll need a pair of these. Come on in. Our oscillator, the mantis, produces a femtosecond pulse train at 800 nanometers, which enters the legend. Here, the pulse train is stretched, amplified, and recompressed to give a 1 kHz train of 109 femtosecond pulses. When the beam emerges from the legend, it is split into two components. The first is destined to be our pump, and passes through the topaz, an optical parametric amplifier that takes the 800 nanometer light and allows us to choose the color we want to excite our molecule with. The second portion of the beam will be our probe, and is directed through a mechanical delay stage that allows us to choose when the probe will arrive at the sample relative to the pump. The beam is then focused down through a sapphire crystal plate where supercontinuum is generated. That is, our 800 nanometer beam becomes a white light beam containing wavelengths from 400 nanometers to 1.6 microns. The supercontinuum probe is then focused down into the sample, overlapping with the pump. The pump pulse arrives at the cuvette first and excites the molecules in the sample. After the sample is excited, molecules' extra energy will start to dissipate and the number of excited molecules decays away. The probe pulse then arrives at the sample at a known time after the pump, and the probe is absorbed by the excited molecules. For every probe pulse that is absorbed by the excited molecules in the sample, an absorption spectrum is acquired. Each spectrum is like a snapshot of the excited molecules at the time delay the probe pulse arrives at. Because the probe pulse arrives at the sample at successive time delays after the pump pulse, there is a decreasing population of excited state molecules to absorb the probe pulse. This results in a decrease in intensity of the absorption spectrum as time goes by. When each of the individual absorption spectra are put side by side, a picture of how the excited molecule is changing over time begins to take shape. This overall picture is what we call a TRA spectrum, and it helps us to develop our understanding of what the excited molecules are doing. What's the connection between transient absorption spectroscopy, squashed beetles, and the girl with the pearl earring? The answer is anthraquinone, a natural red dye molecules extracted from insects and plants. Humans have been using them to paint the town red for more than 3,000 years, and we continue to use them today. Unfortunately, the natural anthraquinones are as fragile as they are beautiful. We all know that colours can fade when you expose them to too much light. What if this happens to a priceless artwork? When light excites an anthraquinone, the molecule has several options for how to get rid of that excess energy, and not all of them are positive. Some will result in fundamental changes to the molecule and the fading of the pigment. The results can tell us exactly which options the anthraquinone takes and why it might choose to take the path that leads to fading. With this information, we can find a way to better protect the pigment, the painting, and if we're lucky, perhaps a way to reverse the damage that's already occurred.
The sun is an abundant source of solar energy, but before we can use it, we need to harvest it. The chemists at the University of Auckland have made a porphyrin fullerene diode which does just that. These solar energy harvesting molecules convert light energy by forming charge-separated states. When the diode absorbs light, an electron hops from the porphyrin to the fullerene, creating the charge-separated state. Ideally, we want the charge-separated state to last as long as possible because the longer the lifetime, the greater the efficiency with which light can be converted to useful energy. TRA allows us to measure how long the charge-separated state exists, so we can fine-tune the molecule to optimize its conversion capabilities.
Right then, see ya!